So welcome to For Calculus 12. Today we're looking at 4.6, exponential and logarithmic equations and identities. We can solve many different equations and identities using logarithms, but if things are in the same base, then you don't necessarily have to use logarithms at all. For example, in part A, we can write 4 as a power of 2, and we can write 1 over 8 as a power of 2 as well. And then just using exponent laws, we can solve for x. So first you can take your exponents and multiply them together, expand the exponents, and you get 2 to the 4x minus 2 equals 2 to the negative 3x minus 6. Now as long as you have one single base on each side of the equation and the bases are the same, then the exponents must also be the same. So 4x minus 2 must equal negative 3x plus 6. Putting all the x's on the left-hand side and all the numbers on the right-hand side, and fixing my mistake with the negative sign, I find that 7x equals negative 4. Dividing both sides by 7 gives an answer of x equals negative 4 over 7. I can check that in multiple ways. First of all, I can plug that number back into the equation. So I can go 4 to the power of 2x minus 1. And I can take negative 4 over 7 and store that as x. And then when I plug in the equation, I get an answer of 0.05. And now if I try the right-hand side, 1 over 8 to the power of x plus 2, I get the same answer. If both of the sides give me the same answer, that means that my solution is correct. The other way to check is to graph 4 to the power of 2x minus 1 along with 1 over 8 to the power of x plus 2, and you have to just be careful with your brackets. And when you graph that, you'll see that it crosses at negative 4 over 7. So let's calculate the intersection. Enter, enter, enter. And the crossing point is negative 0.57. If I change that to a fraction, it's negative 4 over 7. Now in the second equation, everything is in base 3. So I can rewrite 9 as 3 squared. And then just like when I have 5 to the 4 times 5 to the 3, this equals 5 to the 7, I can take these two exponents and add them together because the bases are the same. Okay, now I have a single base on each side of the equation, so now the exponents must be equal. So x squared equals 2 minus x. Whenever I have a quadratic, I'm going to make everything equal to 0 and then factor. I've got two factors, x plus 2 and x minus 1. So there's two possible answers. Either x is negative 2 or x is 1. Now I can't really be sure if both of those are answers until I check, just in case one is extraneous. So 3 to the power of negative 2 squared is 81. 9 times 3 to the power of 2 is also 81. First one works. I'll do the same thing, except for putting 1s in for x. I get 3 and 3. So both of the answers work. And I could also solve that by graphing. Now, if you have a question where the answers are in different bases, or the question is in different bases, that's when we have to use logarithms. So the first thing that you can do is take log on both sides. And you're taking log of everything that's on the left, and that equals log of everything that's on the right. So now we can start to use the log laws that we learned yesterday. Using the power law, the 2x can become a coefficient of the logarithm. But on the left-hand side, we can't take down the x minus 1 because the x minus 1 is an exponent only of 2. So first we have to separate it into two different bases. So first I'm going to use the product law to separate the 3 and the 2 into two separate logs. Okay, that's using law number 1 from yesterday. Then I can use the power law to make the exponent into a coefficient in brackets. Now at this point you could change the log 3, log 2, log 6 into decimals. And then this is actually just a grade 9 problem now. You're just trying to put all the x's on one side. But I want you to be able to answer this using exact answers. So I'm just going to keep the logs in there, but just keep in mind that log 3 is just an ordinary number. So is log 2, log 6. So I'm just trying to get all the x's together. So the first thing that I need to do is expand this log 2 into the brackets. So I get log 3 plus x log 2 minus 1 log 2 equals 2x log 6. I'll rewrite that over here. And now I'm just trying to put all the x terms on one side and all the terms that don't have an x on the other side. So let me move this one. It's being added, so I'm going to subtract it to the other side. So I get log 3 minus log 2 equals 2x log 6 minus x log 2. And this is quite frequently where people get stuck. Do you know what I can do with that x? Factor it out. Take it out of the brackets. Whatever's left over stays inside a bracket. So it's a common factor. And then in brackets, what's left over is 2 log 6 minus log 2. And on the top here, I've got log 3 minus log 2. Okay, so now it's being multiplied. So to move all that stuff on the other side, I'll do the opposite of multiplication, which is divide both sides by log 2 log 6 minus log 2. And you could use log laws to make this all nice and fancy in some simplified form, but actually this is the best form of the final answer. You don't have to simplify this any further. And that's when we can pull out the graphing calculators and plug that in. Log 3 minus log 2. Being crazy with brackets, 2 log 6 minus log 2 gives 0.14. So now I'm going to take that number and store it in x and actually check and see if it works in the equation. So 3 times 2 to the power of x minus 1, and I've stored the answer as x. So that is 1.65. 6 to the power of 2x, I'm hoping is the same answer. Please be 1.65. Yes. I got the same answer when I plug it in for both of the x's. So that means it really must be right. So x is approximately 1.65. Oh, sorry, not 1.65. That's the answer on both sides. Where's my x? 0.14. Thank you. 0.14. Of course, every time I make a mistake, I have to be videotaping. Okay, so that's an exponential equation. In an exponential equation, you start with different bases, and your answer is a lot of logs. The next one is a log equation. When you have a log equation, you start with a lot of logs, and what you're trying to do is you're trying to get rid of the logs. So anytime that you see a log equation, your goal is to have log of one thing equals log of something else. Because if you have log of x equals log of y, that means that the insides have to be the same, that x equals y. So if you only have one log on each side, and the bases are the same, that's when you can cancel the logs. So that's our goal. Our goal is going to be to get one log on each side. So in this question, we've got some problems. On the left side, the problem is we have a 2 out front. And we don't want any coefficients. We just want straight up log. On the right side, the problem is we have 2 separate logs. We want to combine that into one log. So in order to accomplish our goal, we're going to need to take this 2 and put it where? Back in. Okay, basically it's just like the previous example, except for going backwards. We're trying to compress all the logs into one log. On the right-hand side, we can take those 2 logs and we can make them one log. What goes on the inside? Multiplication. 4 times 6 minus x. Nat's on a roll today. Okay, this is the product law. When you have multiplication inside of one log, that can be the same as adding 2 separate logs. So on the left-hand side, the 2 becomes an exponent. So now you can see that we have one single log on each side of the equation. So now the logs can cancel off. So if the log, or if log of something equals log of something, then those 2 insides must be the same. The arguments of the log have to be equal. Okay, so you can cancel the log when you have one single log that's the same base on both sides. And now we've turned a grade 12 problem into a grade 10 problem. So 3 minus x squared, remember, means 3 minus x times 3 minus x. It's not 9 minus or 9 plus x squared, unfortunately. We have to FOIL it out. And expand the 4. To get 9 minus 3x minus 3x plus x squared. Okay, we've got to expand that using FOIL. And then we'll make everything equal to 0. So I'll put the 4x with the other x's. I'll put the 24 with the 9. Let's see, -3, -3, +4 is -2. 9 minus 24 is -15. And now I can factor. What multiplies to -15 and adds to -2? -5, +3. So I have 2 solutions. X is -3 or x is 5. And so, like a good mathematician, I'm going to check those answers. So first, let me store -3 as x. So I'm going to use the original equation. Whenever you check, always check with the original. So on the left side, I get 1.55. And on the right side, I get 1.55. Yes, it works. Now let me try 5. So I'll store 5 as x, and I'll just do second enter to get back what I typed before. So let me try the left side. What? Oh, good thing I checked. What happened? Inside of the brackets is a negative number. We can't take logs of negative numbers. And there's no exponent that will give a negative answer. This answer is extraneous. And the reason why is because the domain of this log is, let's see, what is the domain? We have to be less than 6 or less than 3. We have to have numbers that are less than 3, because we can't have log of 0. So the domain is less than 3. 5 is not less than 3. So, oh, it's x heart. So 5 is extraneous. Okay, now pause the video for a moment and see if you can solve this provincial exam problem using similar principles. So I hope you had a chance to try this problem on your own. The key to this one is changing the 1 to a logarithm. Since the other ones are base 10, we'll change the 1 to log of 10, because 10 to the power of 1 is 10, leaving everything else the same. So just like last time, the goal is to create one single logarithm on each side. So because I've got 2 logs on the right side, I'm going to change that to one single log by dividing the 2 expressions, because subtraction of 2 logs turns into division inside one log by the quotient law that we learned yesterday. So now that I have one log on each side, this is the only time that I can cancel the logs, and the arguments of the log must be the same. X plus 4 equals 10 over 2x. So to solve this, I'm going to multiply both sides of the equation by 2x, and then factor, just like before. 2x squared plus 8x equals 10, so making everything equal to 0. And then factoring out a common factor of 2. 2 goes into everything. So then I look for 2 numbers that multiply to -5 and add to 4. 5 and 1. The 5 should be positive, the 1 should be negative. So there's 2 possibilities. X is 1 or X is -5. So now I have to check. The domain of the log is that x has to be bigger than, well, this one has to be bigger than 0. This one has to be bigger than -4. So when I put those together, the domain is x is bigger than 0. So that means that the -5 is not possible. If I check that one, then I get a non-real answer on both sides. So there's one solution, x equals 1. Let me just double check that one to make sure. Sometimes you'll find that there are no answers. Sometimes both of the answers are extraneous. So it's always good to check. 1 minus log of 2 times 1 is, yay, I get the same answer on both sides. It must be right. And just to show you, if I put -5 in there, I would get non-real answer. So the -5 is extraneous. Okay, turn over to the back side. A very similar question is example 4. One thing that I really don't like is subtracting logs. When I have subtracting logs, then I have to turn it into division, and that means I have to solve rational expressions. So if I can, I'm actually going to make this positive by moving any negative logs onto the other side. Because if I have everything positive, then I only have to do multiplication. It's so much easier. I don't really want to work with fractions. So again, my overarching goal here is to get one log on each side of the equation, because if I have one log on each side and the bases are the same, then I can cancel the logs. So I'm going to combine those logs on the right-hand side using the product law from last class. Because it's adding, I can multiply those two arguments using one logarithm. And now that I have one log on each side, both of the logs have the same base, I can cancel the logs. The insides, the arguments must be the same. And I've turned a grade 12 problem into a grade 10 problem. So expanding, x squared plus 2x equals x plus 6. And I'll make everything equal to 0. So subtract x from both sides, subtract 6. And I have x squared plus x minus 6 equals 0. So now I'll factor it. So two numbers that multiply to negative 6 and add to 1. So the larger one must be positive, smaller one's negative, leaving me with two possible answers, x equals 2 or x equals negative 3. Maybe one of these is extraneous. So let's check the domain. So this one has to be positive, this one has to be bigger than negative 2, this one has to be bigger than negative 6. So that means if I put all those domains together, then for sure x is going to have to be positive. And negative 3 is definitely not positive, so it's not going to work. 2 is the only one that will work. Now how can I check this? It's base 3. Change of base rule. So I can write the left-hand side. Let's see. First I'm going to store 2 as my x value. So I'm going to make 2x. So I can write the left-hand side doing log x plus 6 divided by log 3. That's a change of base. I can divide the two bases, the two logs. And then log of x plus 2 divided by log 3. And then I'll try log x divided by log 3 for the right-hand side. Please be the same. Yay! It works. Another way to solve this is just by graphing. Graph the left side, graph the right side. They'll cross at 2. The next question comes from your homework assignment. So I'm giving you a little advantage on your homework. This one is not the same as any of the ones that we've done so far. It looks crazy. Whenever you see really weird bases, there's a great rule that we can use, which is the change of base law. Just like we did on the graphing calculator, instead of having log base 4 of a, I can write that as log a over log 4. It means the same thing. So log base a of 2a is log 2a over log a. And log base x of 2a is log x over log 2a. Do you know what the right-hand side is equal to? 3. Right. The log base a and the a cancel out. They're inverses of each other. You can also do this by taking the 3 to the front. Log base a of a is 1. Now, do you see what happens on the left-hand side? Log A and log A are the same. They can cancel. Log 2A and log 2A are the same. Anything that's the same on the top and the bottom can cancel. How fantastic is this? Log x over log 4 is 3. So you can multiply both sides by log 4. I can solve this one without a calculator. So log x equals 3 log 4. If I had a single log on each side, then I could cancel the logs. I've got to move the 3 back in if I want to cancel the logs. So I make the 3 back into an exponent. And now I have a single log on each side. They're the same base, so they can cancel, and x is 4 to the power of 3. 4 times 4 times 4 is 64. Isn't that rewarding? Isn't it pretty? I mean, math is beautiful. So you can solve any of these equations using your graphing calculator. All you have to do is graph the left-hand side and the right-hand side. Now when the base is different, you're going to have to use a change of base rule. And the nice thing about graphing with your graphing calculator is your calculator will never show you extraneous solutions. It'll always be able to show you how many answers there are, and it will never show you any of the wrong answers like when you solve it by hand. So why don't you give this a try, see if you can find an appropriate window, and we'll come back to it again in about 5 minutes. And we're back. So this is tedious to plug into your graphing calculator, but it pays off because you don't have to worry about extraneous roots, and it's an excellent way to go through your test when you're finished and just check to make sure that your answers are correct. You have to be a little bit careful with your brackets, especially if you have more than one term in the numerator or denominator. Luckily, we don't have to change the window. There's our sum of the logs. There's the number 1. And when you calculate the intersection, it crosses when x equals 1. So let me just graph that here. We've got the logs. We've got the horizontal. The intersection is at the point 1. And that's just a standard window from -10 to 10. So the next 2 questions are also from your homework assignment, and they're much more challenging because the first one is a log inside a log inside a log. There are no log laws that will help you to solve this one. So basically all we need to do is move the log to the other side of the equation, one at a time. So we're going to start with this log here, and we're going to move it to the other side of the equation. Okay, if you have a log on one side, on the other side you have an exponent. The base of the log becomes the base of the exponent. What happens to the 1? So on the left side, we're left with log base 4, log base 2, and x. And when we move a log to the other side of an equation, everything on that side gets pushed up into the exponent. Okay, the 1 becomes an exponent. So that means log base 4 of log base 2 of x is just a half to the power of 1, which is a half. Okay, now we'll do the same thing again. To move the log base 4 to the other side of the equation, it becomes a base which pushes the 1/2 up into the exponent. And on the left side, we're just left with log base 2 of x. Do you know what 4 to the power of a half is? 2. So log base 2 of what number equals 2? Log base 2 of 1 is 0. Log base 2 of 2 is 1. How do we get 2? Moving that log to the other side pushes the 2 up into the exponent, leaves the x by itself, showing that x is 4. This is kind of hard to check as well, unless you have a calculator that has different bases. Okay, and the last question, it's difficult because we have 2 different bases. So I can't put those 2 logs together. Instead, I have to do the change of base. So log x divided by log 9. And that 3 is the same as 3 over 1. So if I was writing it as a fraction, it would be 3 log x over 1 log 3. I don't really need to write that 1. And I can only add those 2 fractions if I have a common denominator. So I need to somehow turn log 9 into log 3. Yeah, I can write 9 as 3 times 3. So I can write 9 as 3 squared. It's still not quite the same. I only want log 3's. So I have to use another rule, which is the power law. Take the 2 and make it a coefficient. Now there's a bunch of things that you could do. Do you know how to get rid of the 2 on the bottom there? What would Miss Jones say, Mrs. Jones? I don't know if you can see this, but when I look at this, I see 2 common terms of log x over log 3. You can even think of log x over log 3 as like the letter a. So really this is like half a plus 3a. Okay, the first term is like a half, and then the second term is 3. But maybe you don't see like I do. So anytime you want to get rid of a number that's in the denominator, another thing that you could do, I think this might be what you would have done last year, is you could multiply everything by that number. You've done that before, right? And while we're at it, why don't we multiply by the log 3 as well? Just multiply by everything in the denominator. And at least that gets rid of the denominators. So then the log 3's would cancel, the 2's would cancel, and you get log x plus 2 times 3 is 6 log x equals 14 log 3. So 1 log x and 6 log x's are 7 log x's altogether. You can think of log x as x. 1x plus 6x. And that's 14 log 3s. So if I divide both sides by 7, I get log x equals 14 divided by 7 is 2. I'm sorry if you're running out of space. So now again, I could solve this without using a calculator by moving the 2 back inside. To make one single log in the same base on each side, which can finally cancel, leaving x equals 9. So your homework for today from the Michelson book is to try page 183, numbers 1 to 7. And some of these ones we already did together in class. If you have any questions, you can send it to me on Edmodo.